Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 12, Lesson 1 on Probability Basics. So we begin our unit on probability today, which is really one of my favorites because of how often probability calculations come up in the real world and how often you see them. Whether you're looking at a weather forecast and you see that there's a 60% chance of rain, whether you're watching sports and you see that a hitter has an average of 0.3, 10 or something like that, right? You're dealing always with probability and trying to do what I call quantifying chance. So let's jump right into it and let's talk some probability. Now today we're going to introduce you or remind you of a lot of important terminology that goes along with probability. But let's begin by just talking about probability a bit. Mathematics seeks to quantify and model just about everything. Now, one of the greatest challenges is trying to quantify chance, right? Like uncertainty. That is exactly what probability seeks to do. With probability, we assign a number to how likely an event is to occur. Terminology in probability is important, so we introduce some basic items here. Let's get right into them. Basic probability terminology. To begin, we have an experiment. Now, this isn't a scientific experiment per se, but an experiment is just some process that occurs with well-defined outcomes. 2. An outcome is a result from a single trial of the experiment. 3. Equally likely outcomes, when the outcomes to an experiment all have the same chance of occurring. 4. An event. An event is a collection or a set of one or more outcomes. And finally, sample space. That's a very important piece of terminology. It's the collection of all the outcomes of an experiment. All right, now a lot of probability, you don't really particularly need to know this terminology, but as you move through this unit, this terminology becomes more and more important in terms of helping us really understand, quantify, and sort of collect our knowledge about probability. So let's jump into exercise 1, which should be a fairly easy problem that you probably could have done when you first learned about probability. An experiment is run whereby a spinner is spun around a circle with 5 equal sectors that have been marked off as shown. Letter A, what is the experiment? Right? And again, we oftentimes think of experiment in terms of science, right? Oh, I'm going to put one chemical and another chemical into a beaker and see what compound I get. But in this case, the experiment literally is spinning the spinner, or arrow, once. And noting the number it falls on, or the number it points to. All right, very simple, right? Spinning the spinner once and noting the number it points to. Letter B. Give one outcome of the experiment. Well, remember, what an outcome is literally something that can happen when you run the experiment once. Well, quite frankly, one outcome of the experiment could be any number from 1 to 5. And maybe I should be a little bit better than that given that we're in Algebra 2. Let me say any integer. Because I don't want you to think that you can get 3.5. I don't want you to think you can get pi or the square root of 2. Any integer from 1 to 5, or any whole number from 1 to 5. All right, letter C. What is the probability of spinning the spinner and landing on an odd number? What is the event here? What outcomes fall into the event? All right, now what I'd like you to do is pause the video right now and just answer the first part of this question. What is the probability of spinning the spinner and landing on an odd number? Because unless you've missed probability all these years throughout all the courses that you've studied probability in, you're going to be able to answer that question. All right, so almost everybody on this question is going to say, well, there are 5 possibilities, there are 3 odd numbers, so the probability of landing on an odd, and we kind of use function notation when we do probability. Probability of odd will be 3/5, and a lot of math teachers, a lot of students will say 3 out of 5. All right, but we represent, remember, we want to assign a number to probability, and 3 out of 5 is not a number, but 3/5 is. Now, let's talk about events and outcomes, right? The event, right? The event, which is a collection of outcomes, the event is falling on an odd number. Right? That is the event. Okay? And what outcomes fall in the event? The outcomes that fall in the event are obviously 1, 3, and 5. And they're all equally likely outcomes. All 5 of them are all equally likely outcomes because this is evenly divided up. That piece of terminology, equally likely outcomes, is going to be a very, very important one throughout probability because it's going to allow us to say, well, we have this many equally likely outcomes in total. That's what's called the sample space. And these are all the equally likely outcomes that fall into the event that we're trying to quantify the chance of. All right, let's keep going and let's define a basic formula for probability. The answer from that last exercise helps us to define the basic formula that dictates many probability calculations. Many, right? So let's take a look at it. The basic definition of probability. The probability of an event E occurring is given by the ratio P of E equals N of E divided by N of S, where N of E is the number of equally likely outcomes that fall into event E, and N of S is the number of equally likely outcomes that fall into the sample space. Now again, notice how we kind of use function notation here, and it really is function notation, right? The input to our probability function is the event E. The output is given by the ratio of two functions. You might call them the number functions. N of E is simply the number of equally likely outcomes that are in this experiment that fall into the event we care about. And N of S is the number of equally likely outcomes that are in the entire sample space. The sample space, remember, is all possible outcomes to the experiment. Let's take a look at exercise number 2. Given the above definition, between what two numbers must all probabilities lie? Explain. Well, I know that this is a question you've contemplated before or thought of before when talking about probability. So I'd like you to pause the video right now. And remember, I'm talking about numbers here. Between what two numbers must all probabilities lie given this definition? Pause the video now and see if you can give me an answer. Well, I'm hoping that you said that all probabilities lie between 0 and 1. All right, but I really want to justify this using some algebra. Between 0 and 1, what's called inclusive. And what that means by inclusive is that it includes 0 and it includes 1. Now, you might realize that just because of past experience you've had with probability, but let's really kind of like explain it using that formula. And it's pretty easy, and here's why. Remember, N of E is the number of equally likely outcomes, right, that fall into the event that we care about. Now clearly, N of E must be greater than or equal to 0. All right? In other words, you can't have negative outcomes. I mean, you can have negative outcomes, but you can't have a negative number of outcomes that fall into a given event, right? So this is definitely true. All right? But the other thing that's definitely true is that the number of equally likely outcomes in our given event must be less than or equal to the number that fall into the entire sample space. And that should make sense, right? Because the sample space includes all the outcomes, so the number of outcomes that fall into the event that we care about must be less than or equal to N of S. Now, one of the golden rules of inequalities, which is what these two things are, is that we can divide both sides of an inequality by any positive number, and it doesn't change the inequality. Now, if we divide an inequality right by a negative number, then we got a problem, All right, because then it flips the inequality. Don't worry about that right now. So what I can easily do is I can take these two things and I can divide them both by n of s. Right? So let me just do that. Let me divide both sides by n of s, the number of outcomes in the sample space. Now keep in mind, again, that also has to be a positive number. But both of these two things on the left-hand side is the definition of the probability of E. Right? The probability of E is n of E divided by n of s. So the probability of E, 0 divided by anything, is 0, except for 0 divided by 0. So the probability of E must be greater than or equal to 0. And of course, n of s divided by n of s is equal to 1. So the probability of E must be less than or equal to 1. Therefore, right, the probability of E must be greater than or equal to 0, less than or equal to 1. Oftentimes, this is all wrapped up in a single statement that kind of looks like this. But you can think about it really as these two inequalities or this one compound inequality. In other words, all probabilities are wedged between 0 and 1. Basically, 0 probability saying that an event is impossible, and a probability of 1 meaning that an event is inevitable, right? It's going to happen, okay? And that's great, because that gives us these two borders on chance. Either something is definitely not going to happen, or something definitely is going to happen, right? And then everything else between is this sort of shade of gray, right? And it allows us to then start to think about, well, if the probability of it raining outside is 35%, which is 0.35, it's not 35, it's 0.35 on our probability scale, well, then we should make decisions based on that. All right? So let's talk about theoretical probability. There's two types of probability that we're going to be looking at throughout this unit and our next unit on statistics. One's called theoretical and one's called empirical. We'll get to empirical at the end of this lesson. But theoretical probability, when we work with theoretical probability, we don't have to run the experiment to determine the probability of an event. We simply must know the number of equally likely outcomes in the sample space and the number of those outcomes that fall in our event. Let's look at a more complex experiment than just spinning a spinner around once. That's not very interesting. Exercise number 3. A fair coin is flipped 3 times and the result is noted each time. So that's our experiment, right? The sample space consists of ordered triples such as h, h, t, which would represent a head on the first toss, a head on the second toss, and a tail on the third toss. Letter A. Draw a tree diagram that shows the different equally likely outcomes in the sample space. All right, so sometimes when you get what are called compound experiments or compound events, it starts to get harder to think about what the equally likely outcomes are. And a classic example is flipping a coin multiple times or rolling a die multiple times, or maybe flipping a coin and rolling a die, right? So those are compound events because we're doing something more than once and we need to collect those things, right? So tree diagrams are one really nice way of sort of visualizing the outcomes to these compound experiments. So let's take a look at a tree diagram for flipping a coin 3 times. All right, so what we do is we say to ourselves, the first time that I flip the coin, I can get a head or I can get a tail. And that is literally sort of, if you will, flip number 1. Okay, now if I get a head on my first flip, then on my second flip, I can get a head or a tail. And if I get a tail, then I can get a head or a tail, and that's flip 2. Now, of course, I have one more flip, and if I got a head on my second flip, I could get a head or a tail. A tail, I could get a head or a tail, and likewise, head or tail, head or tail. Now, sometimes students get a little bit confused about tree diagrams, which is very understandable. You don't use them a lot in math because we don't spend a lot of time at either the middle or high school level on probability. And it's kind of hard to get good at something if you don't spend a lot of time on it, right? But I do want to point out how we can really kind of think about this. Like for instance, going back to this particular outcome, right? Getting a head on the first flip, a head on the second flip, and a tail on the third flip. I can actually show you that path along my tree diagram, right? That is a head, and a tail. That would be that particular path, all right? Now don't confuse that with just getting two heads and a tail. There's lots of these paths where you got two heads and a tail, right? Another one would have been getting a tail on the first one, a head on the second one, and a head on the third one, all right? Both of those would fall into the event getting two heads and a tail. Now, if the event was getting a head, and then a tail in that order, there's only one event that falls into that, or one outcome that falls, into that event. Now, one way to kind of think about the outcomes of a compound experiment is the tree diagram. Another way is literally to list out what are called ordered pairs or ordered triples or ordered quadruples, depending on how many stages there are. This is a three-stage experiment. How many stages there are in your experiment. So let's actually list all of these things out. And it's a little bit of a pain, but we can be very systematic about it. So here we go, right? So I could have gotten a head on the first one, a head on the second one, and a head on the third one. Or I could have gotten a head on the first one, a head on the second one, and a tail on the third one. Or I could have gotten a head on the first one, a tail on the second one, and a head on the third one. And then I could have gotten a head on the first one, a tail on the second, and a tail on the second. Now that's not all of them, because I want you to actually fill in the rest, but then it's all of them that kind of came from this half. In other words, those are all of them where I got a head on the first one. So I got head, tail, head, and head, tail. What I'd like you to do is pause the video and write down all the ordered triples that you would get from this half of the branch or the tree. All right, let's do it. So again, I can just kind of be systematic about it. I could get a tail, then a head, then a head. I could get a tail, then a head, then a tail. I could get a tail, then a tail, then a head. And I could get a tail, and a tail, and a tail. And again, for me, I just literally walked down the branches. So I went tail, head, tail, head, tail, head, and tail, right? It also asks how many are there. There are 8 total. So there are 8 total equally likely outcomes that have occurred in this experiment. Now, because we've got the sample space, here it is, right? This is our sample space. This is absolutely everything that can happen in terms of equally likely outcomes, right? We know n of s, it's 8. We can now start doing some probabilities. So let's take a look at letter C. Find each of the following probabilities based on your answers from A and B. I, probability of all heads. Well, again, right, this is simple. The event now is all heads. How many of our equally likely outcomes fall into this category? Well, just one, right? It's right there. So n of E is 1, n of S is 8. So obviously, the probability of all heads is 1/8. All right? Number 2, the probability of exactly 2 heads. Exactly 2 heads. Well, that can actually happen in quite a few different ways, right? Let me really highlight them here. Right, exactly 2 heads. Here's one, and here's one. Right? So there are 3 equally likely outcomes that fall into the event exactly 2 heads. So n of E is 3, n of S continues to be 8, so our probability is now 3/8. And finally, number 3, the probability of all heads or all tails. Well, right, there are 2 that fall into that, all heads and all tails. So the probability of all heads or all tails is 2/8. Now for some of us, we might not be able to help ourselves and we have to reduce that down to 1/4. How do you leave your answer? Well, some math teachers actually really like it to be left unreduced because then you can see the total number of outcomes in the sample space and you can see how many of them fall into the event. Other math teachers are insistent that you reduce. So make sure you check with your own math teacher to see how they would prefer it. If this was, let's say, on the New York State Algebra 2 Regents exam, they probably wouldn't give a question this easy, but they would take, if it was free response, either one of those answers because they are equivalent. All right, let's keep going. And let's talk a little bit about empirical probability. Sometimes we must quantify chance by using observations that have been made in the real world. Yes, the real world, as opposed to the fake world. In this case, we talk about empirical probability. The fundamental equation for probability still applies. N of E divided by N of S. So let's take a look at exercise number 4. A survey was done by a marketing company to determine which of 3 sodas was preferred by people in a blind taste test. The results are shown below. All right, so let's just make sure that we kind of understand this. This marketing company came along, right? They had 53 total people. They gave them soda A, soda B, soda C. 18 of them preferred soda A, 24 preferred soda B, 11 preferred soda C, right? And again, this now allows us to quantify the chance that if we picked a person at random, right, what the probability would be that they would prefer one of these particular 3 sodas. Let's take a look at letter A. Find the empirical probability that a person selected at random from this group would prefer soda B. Express your answer as a fraction and as a decimal accurate to 2 decimal places, which is the standard. All right, so this is easy, right? The number of people or the number of outcomes that fell into the event of preferring soda B is 24. The total number of outcomes is 53. So maybe I would write it like this, whoops, and maybe I will do this. The probability of B, right, would be 24 divided by 53. Now, a lot of times, we like to turn probabilities into either decimals or percentages. All right, and that's very understandable. Like, it would drive me crazy if the weatherman was like, well, the chance of rain today is going to be 24 out of 53, right? That I just know, I don't want that, right? So what I want is I want the chance of rain is going to be 75% or it's going to be 15% or something like that. A lot of times we express probabilities as fractions, sure, because that tells us how many out of how many, right? But many times we also want it in terms of a decimal, which is basically the equivalent of a percent, just not multiplied by 100. Now, obviously, you should all know how to take your calculators and go 24 divided by 53. One thing that's a little bit weird, especially on the TI Inspire, is that you have to hit second enter in order to get the fraction to be represented as a decimal, because otherwise it'll just reduce it as a, or express it as a reduced fraction. But in this case, accurate to 2 decimal places, it's 0.45. And not surprisingly, the reason that that is typically the standard, right, is that then that tells us that we're looking at 45%, right? 45 100ths is 45 out of 100, which is 45%. Let's take a look at letter B. Find the empirical probability that a person selected at random from this group would not prefer soda A. Again, express your answer as a fraction and as a decimal accurate to 2 decimal places. All right, well, pause the video now and go ahead and try to figure out this probability. Right? Well, a lot of times, we're going to write these things in terms of function notation, right? We want the probability not A, which really means we want the probability of B or C, right? So all I need to now do is just add the number of people that liked B and C together, divided by 53. So that is going to be 35 divided by 53, and that is our fraction. And we won't go back to the calculator now because that seems a little silly. but in terms of a decimal, 0.66. Or 66%. But again, they asked it for a fraction and as a decimal, accurate to 2 decimal places. All right. Now, there was probably nothing that we saw today, including the terminology, that you didn't see in Algebra 1, right? Even the tree diagrams and more complex probability problems, you've already worked with a little bit. But we want to be comfortable with the terminology, with the notation, with ways of like drawing tree diagrams and ordered triples and things like that as we move through this unit and we attack slightly harder probability problems. Nothing we're going to do in this unit is going to blow your mind, probably. It's not going to be all that difficult. But we do need a real baseline understanding of probability before we start using it a lot more in our next unit on statistics. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.